All right, welcome back to topic 11.6, which is Kirchhoff's loop rule. This is daily video number 1, where we discuss the conservation of energy and how that leads to Kirchhoff's loop rule. And we're also going to look at some graphs of voltage versus position in the circuit. My name is Dr. Kelly Miza. I teach at Delaware Valley Regional High School in Frenchtown, New Jersey. So let's review, first of all, before we go on. Energy! Back in our first unit or two, the electrical potential energy of a situation was Q times the electric potential difference. So when we're talking about conservation of energy or a change in energy, we can also talk about a change in potential. And that's how we discuss these things in circuits, because it's a lot easier to talk about change in potential, aka voltage, than it is to talk about energy. And that's where this Kirchhoff's loop rule comes in. So what this says is if a single charge makes a complete loop around the circuit, conservation of energy says your change in energy is zero. Or in circuit terms, a single charge has energy Q delta V. So if your change in energy is zero, that means your change in potential is zero. So it's kind of like physics 1, right? Like if you were going to lift something up and then put it back down again, its total change in gravitational potential energy would be zero. It ended at the same place that it started. So that's what Kirchhoff's loop rule is saying. Is it's saying, hey, if you make one complete loop around a circuit and come back to exactly where you started, your change in energy, your change in voltage, your change in potential is going to be zero. If we look at this again, we gain voltage from the battery, we lose voltage from the resistor, and we get back to where we started. Plus voltage battery minus voltage resistor has to equal zero. I end up back where I started. So just like with gravitational potential energy, zero is your choice. And this choice is going to end up being important in our next video, daily video 2. So just keep that in mind. But this is nice because it allows us to make some conclusions such as, okay, the voltage across the resistor is the same as the voltage across the battery, which we kind of already knew because they're in parallel, but making it more official. All right, so let's look at this lovely graph and this lovely circuit here. So right here, we have a graph of potential difference measured from V equals 0 versus the position in the circuit. So if I look at my graph, point A is what we define to be 0. So point A has a voltage of 0. Great. Then we go through the battery and we get to point B. And now we're at some higher voltage. And then we're chilling at that same voltage until we get to point C. And then we lose some voltage to get back down to D, which is at potential 0, which makes sense. Your batteries give you voltage. Your ideal wires all have the same voltage as we go from point B over to point C. And then our resistors take away voltage. And now we're back down to where we started. Boom, boom, boom. If this is all at the same potential of 0. Neat. All right, let's look at an example, shall we? We have this circuit. So we have 5 resistors in series with our lovely battery, and we have made a voltage versus position in circuit graph. So our first question is, which resistor has the greatest resistance? So if you remember, resistors in series, they have the same current. So the only thing that's going to be different for all of these little resistors is the voltage drop across them. And from Ohm's law, V equals IR, if I have the same current but more resistance, that means my voltage is going to be larger across that resistor. That resistor is going to have a larger potential drop. So if I look at our graph, B to C has a big boost, but that's the battery. So after that, we're going through each individual resistor, and I'm looking for which resistor has the largest drop. And that's going to be this guy between J and K, which is going to be R4. What's the voltage of the battery? Well, my battery goes between B and C. So if I look at our graph between point B and point C, that's a boost of 11 volts. Our battery has a voltage of 11 volts. So what should we take away? A complete loop around a circuit has a potential difference of 0. If you end where you start, your potential difference is 0. Any boosts you got are taken away, and now you're back at 0. This sounds redundant, but it's going to make a difference soon, I promise. And with that, thank you. So this was Kirchhoff's loop rule. Next time, we're going to talk about Kirchhoff's junction rule, and then we're going to put them all together, and it's going to be a great time. See you then.